I'd like to now talk about Saturn, another very, very interesting object. Its diameter is 60,000 kilometers, which is 19.5 times the diameter of the Earth, but it has a very, very low density, only 700 kilograms per cubic meter. What this means is that if you actually could imagine an object the size of Saturn, and you had with a density like that, and you could actually take that object and place it into water, assuming that you had an awful lot of water. So you've got the planet Saturn with its rings around there, and you dump that into a huge vat of water, Saturn would float rather than sinking in the water. Water has a density of 1, or 1,000, I should say, 1,000 kilograms per cubic meter. Saturn is only 700 kilograms. So it's much lighter than, it's much less dense, I should say, than water. And so that material would actually float in water. Of course, it wouldn't really, because it's very, very cold. It would just freeze the water. But, just based on density considerations alone. It's made of hydrogen and helium, but it's less compressed than Jupiter, which is why it has a much lower density. Its rotational period is 10 hours and 14 minutes at the equator, 10 hours and 40 minutes when we go to higher latitudes or lower latitudes. And the core is actually rotating at 10 hours and 46 minutes. So variations in speed were registered by the Cassini-Huygens craft, and they're probably due to interactions between Saturn's magnetic field and one of its moons called Enceladus. So Enceladus and the magnetic field interact, and this actually produces this differential in rotation. Saturn is more pancaked than Jupiter is. So that is to say that it's more flattened than Jupiter. But again, just like we said with Jupiter, when you actually calculated Jupiter's amount of flattening, it's still not as much as would be predicted, and then based on the rate of spin. So again, this suggests the rocky core. And in this case, the rocky core, because of the increased flattening, is even bigger than the core of Jupiter's. So it's believed that Saturn's core, even though it's a smaller planet, is 1.5 times that of Jupiter's core. And the core itself is 15 times the mass of the Earth. Saturn's ring system is certainly the most spectacular one in the solar system. At some points, and again, I'm not really good at drawing this, but if you imagine Saturn looking something like I've drawn here, that's showing the rings being more or less oriented towards the Earth, but this, as it moves around its orbit, the position of the rings change. So at some point in time, the planetary ring system is going to be very, very thin, and you're not going to see it like that, but if you can see it almost edge on, and the rings appear to be, if you're using an Earth-based telescope, a small telescope, you won't see the ring at all. So the ring is actually quite, although the ring system is quite wide, it actually gets to be very, very, the thickness is very small, and it's only somewhere between, at various points, it's been measured to be between 10 and 15, not kilometers, but meters in thickness. So it's amazing that you could see it at all when it's oriented in this position. During Saturn's summer and winter, that's when the rings appear brightest to us. So it's during the summer and the winter when they're oriented more or less in this direction, and then during the fall and the spring, they nearly disappear. The rings have a diameter at the outer extremes of about 200,000 kilometers. So we're talking about thickness only 10 to 15 meters, but from one end of the ring system to the other end, 200,000 kilometers, or 200 million times the thickness of the ring. Saturn also the rings of the surface of Saturn has bands, just like Jupiter has bands. So we've got again that kind of alternating various colored bands, but they're not as colorful as those on of Jupiter, and there are no features like spots that we see on Saturn. Saturn's atmosphere consists of 92.4% hydrogen, and the remainder of the atmosphere is 7.4%. That's a 4, not a 9. 7.4% helium, and there are still significant amounts of other gases. There's 0.2% methane. So these have all been measured fairly carefully, and 0.02% of ammonia. Now it's believed that maybe there might have been more ammonia, but it's believed that solar radiation has actually broken the ammonia up into nitrogen and hydrogen. And both of these gases have probably just gone out into space. So we do have a little bit of ammonia present there. The concentration is much greater near the planet's center of these gases than it is out as we go further out. Saturn's atmosphere is like Jupiter's, but there's thicker clouds due to the fact that there is a weaker gravitational field. The stratosphere is about 200 kilometers. From the surface, the troposphere is about 50 kilometers up, and it's kind of a haze, sort of a thin haze. There's an ammonia ice layer from about 50 kilometers to around 25 kilometers. From 50 to 25 kilometers is the ammonia haze. And then from about 175, a thickness of 175 to 225 to 200 maybe 250 kilometers below that, there's a layer that's ammonium hydrogen sulfide again, that NH4HS. That's an ice layer, and below that to about 300 kilometers is a frozen water layer. There's a zonal flow like Jupiter, but it's stronger than Jupiter's. East-west wind velocities can actually get as high as 1,500 kilometers per hour. So this is roughly 900 miles per hour. So this is enormous, almost 1,000 miles an hour. This is enormous. These are actually enormous velocities, unlike anything probably that you see anywhere else in the solar system. There's lightning discharges that have actually been observed. And Saturn, I didn't mention this, but you also see that this has also been seen on Jupiter, but I think it's even more profound on Saturn. You also see aurorae, like we have on Earth, the aurora borealis, and they're very, very bright, and these have actually been photographed. Another interesting thing about Saturn is that, in all probability, if we look at actually the composition of Saturn, it's got a larger core than Jupiter, which is kind of an icy, rocky core. So the rocky, kind of a silicate core surrounded by ice, and then a thinner metallic hydrogen layer than that of Jupiter. The core pressure is only 1/5 that of Jupiter, but it's still at that pressure, it's still well over 1 million atmospheres, and it's still that is still 2 to 3 times the pressure of the core pressure of the Earth. And in all probability, helium actually is precipitating out from Saturn's cooler outer layers, and it's falling as a light shower of helium droplets to the planet's interior. As it sinks, it's actually getting compressed by the gravitational field of Saturn, and while that's happening, that causes a certain amount of heating to occur. Now, Saturn has a magnetosphere, but as I said, because there's no it doesn't have a plasma torus like Jupiter does, because of the Io is actually moving at a distance where the field is strong enough to create this plasma torus, but there are no moons actually orbiting around Saturn at the point where that would actually occur. Now, Saturn has rings that are really, as I said before, quite spectacular. Using an Earth-based telescope, you can easily see 3 of the rings, and with a more powerful one, even a 4th ring. So these rings are designated from the outside to the inside, A, B, C, and D. And then you also get other features that you see are in the outer A ring. That seems to be split, and there is a 300-kilometer wide gap in it called the Encke gap. And then on the outer, that's on the outer part of the A ring. And then there's also another a much larger gap, about 4,500 kilometers, that you can actually see from the Earth fairly easily, even with a smaller telescope. You see what's called the Cassini division between the A ring and the B ring. Other rings designated D through G were discovered much later. These were discovered by some of the flybys that we've had. The kinked braided structure of the very, very narrow F ring is actually caused by, and this is only 100 kilometers in width, and it's caused by 2 small moons that are orbiting that are actually orbiting the rings, orbiting within that ring system, and these are referred to as shepherd moons. And they seem to actually be pushing the very small rocks or icy particles that make up the rings, and are actually shepherding them and pushing them together, preventing them from spreading out. The rings are composed of smaller particles. As I said before, it's probably water. It's probably ice made out of water, and these tiny particles can be anywhere from sub-millimeter in size up to probably some of the larger ones could be as much as 10 meters across. And as I mentioned before, the rings are only about 10 to 15 meters in thickness. There are a couple other things that I want to say about Saturn's moons. And one of these, well, it's something that I want to talk about moons in general. When moons are actually orbiting whether it's a planet or moons or planets orbiting a star, what you have is there's a point at which, when these things are actually forming, where these things are actually there's 2 forces that are in balance. One of these is the gravitational force, which is tending to push all of the matter of this, whether it's a moon or a planet, as it's beginning to form, as it's beginning to solidify. It's holding all of that together. But you also have the gravitational tidal forces of whatever this thing happens to be orbiting around. So we know that there are tidal forces from the Earth that influence the moon. There are tidal forces from the gravitational pull of the sun that are influencing the Earth, and there are certainly tidal forces from the planet Jupiter that are actually influencing all of its moons. There is a certain distance that you get from the moon where the tidal forces become so from the central object, rather, not from the moon, but from the central object. So the moons, when they're at a certain distance from whatever it is that they happen to be orbiting, the planet that they're orbiting, we have something called the Roche limit, R-O-C-H-E. And the Roche limit, assuming that the moon and the central planet are made out of the same material, the Roche limit tends to be about 2.4 times the diameter of the planet. That's at that point. That's where we actually get to the point where the gravitational field is actually going to be strong enough that it would actually rip the moon apart. So when you get to within approximately 2.4 planetary radii, that's where the moon's going to fall apart. And that's really what apparently happened to one of the primordial moons of Saturn. It got a little bit too close to the planet. It was pulled apart, and in being pulled apart, it formed the ring systems of Saturn. There's also a lot of literally thousands of narrow, what are referred to as ringlets, or the rings themselves being composed of thousands of narrow ringlets. And that's probably caused by 20 or 30 these little ringlets, which you can't see until you get much closer to the planet. These ringlets are actually caused by the movement of some very, very small, maybe 20 to 30 of the smaller moons that are actually orbiting within the ring systems. There also are what appear to be radial spikes that are if you look at the rings themselves, there are these areas that look like spikes that are radiating out in this direction, and the spikes are actually caused by very, very small dust particles. Okay. Saturn has at least 61 moons. The 8 largest are actually, you can find them in table 12.3 on page 298 of your textbook. I don't want to spend a lot of time on these things. I want to talk about one principal, the largest moon, which is Titan, and I also might refer to one of the other moons as well. But you can, if you want to get a complete listing, the other moons, I said the 8 largest are actually named. The other 53 moons, some of them may not be named. One of them, I think I have the name for, but the other ones are probably not listed in your book. Let's see. Titan, I said, is the largest moon, certainly the most interesting one. It was discovered by Christian Huygens in 1655 from the Earth with an optical telescope. It appears as a not well resolved, it's barely resolved, reddish disk. The red color we now know, interestingly enough, is actually due to the fact that this moon has an atmosphere. So the other moons do not, but this one, we're not talking about a thin atmosphere, but actually a relatively thick atmosphere. So this isn't like the kind of thin atmosphere that we saw before, which is a temporary atmosphere that's due to outgassing from the interior. But this one, it's thicker and denser than the Earth's atmosphere. It consists of 98% nitrogen and 2% methane with traces of argon and some other gases. At 400 kilometers above Titan's surface, there's an ultraviolet absorbing haze. At about 300 kilometers, there's another haze that absorbs both in the UV and in the optical or visible region. From about 200 to 100 kilometers above the surface, there's a thick aerosol, a type of haze, and then there are scattered clouds, and these are these are not water vapor clouds, but clouds of liquid methane that form about 10 to 20 kilometers above the surface of Titan, and a rain of methane actually falls to the moon's surface. The surface temperature is about 90 to maybe 100 Kelvin, and the pressure is 1.6 atmospheres. So imagine this. We've now got something that still pretty cold. So we're looking at temperatures much colder than we would ever see anywhere on the Earth, and probably something on the order of I don't know what the coldest temperature we've ever observed on the Earth is, but I would imagine this is probably somewhere at least 100 Kelvin below that. But the pressure is only 1.6 atmospheres, so that's kind of interesting. Titan's density is 1,900 kilograms per cubic meter. It consists of a rocky silicate core surrounded by a thick, high-pressure ice layer, a thicker liquid water layer, and then a near the surface ice layer. So all of this stuff is screaming the possibility of, again, a place where you might want to, at some point in time, actually look for the presence of some form of life. So as I said, I'm going to skip the other Saturn's other medium and small moons, basically because of time restraints, certainly suggest that you read these in your book. There's two other things that I do want to talk about, though, and one of them is the fact that there is a kind of a very, very diffuse ring, which was not known until one of the flybys. This couldn't actually be observed. It's very far from the planet. So if you look, and I don't remember what page it is in your textbook. Let me see if I can find this. Yeah, if you look at page 308, you'll see a picture that actually shows as a very, very small object Saturn and its ring system. It's, let's say, A through G ring system, as something that's almost the size of a dot. So I'm going to blow that up a little bit. But here's Saturn and its rings. And then around that is something probably that looks like this. And this is this very, very diffuse ring that lies well outside of the other rings and is much, much wider than all of the rings and the planet itself combined. So that's just something that I wanted to point out. And then there's one other thing that I wanted to say, and that will conclude the lecture. And that is the fact that if you actually have planets or planetoids or moons or whatever that are moving around another object, you sometimes have a synchronicity in the way that these things orbit, even though they're not orbiting in the same, they're orbiting at different distances. You'll get a synchronicity where these things, and I'll give you an example which actually has to do with Saturn itself. So there are 3 moons of Saturn that move, that have this kind of synchronicity in their movement. So we've got Saturn and its rings, and then very, very close to this, we have a moon called Telesto, and then we have another moon called Tethys, which is orbiting out here, and then we've got another moon, and I don't remember where, so Calypso is out here somewhere. This is Calypso, and so that's going around like this, and Telesto is going around like that, and then we've got an outer moon called Tethys. Tethys is larger than the other two, and what's happening is that these two things are actually orbiting in synchrony with, that is Calypso and Telesto are orbiting in synchrony with Tethys. But the angle, I didn't draw this very well, so you can't really see this. But if you would extend all these out in the same distance, you would find that this is a 60-degree angle, and that's a 60-degree angle. So these 60-degree kind of spikes that you have here are something that were originally observed by Lagrange, and they're called Lagrangian points. I think that's the last thing I want to say in this lecture. It's a lot of information, but remember, once again, I'm only going to ask you about the stuff that I talked about. But again, I encourage you to read everything in the book. I mean, it's actually very, very fascinating, these 2 chapters. Thanks again for your attention, and I'll see you next week.